Okay, so now this process is long and challenging and difficult, and well, not really difficult, I guess. It's just a matter of you keeping track of all the variables you have and the process, and just kind of going through the process. And you'll find at the end the real power of this is once we've simplified this whole process, which you're going to see, then it's just a matter of adding or subtracting really tiny values of h at the end, instead of doing the slope calculation 4, 5, 6, or 8 times. Okay, so it's a lot more swift once we finish with this simplification process. Okay, so this example now, we're going to find the, of course, estimate. Please don't forget that word, the estimate of the instantaneous rate of change of the function f of x equals x squared plus 4x minus 3 at x equals negative 1 using the difference quotient. Okay, so the average rate of change is f of a plus h minus f of a all over h. Okay, because we know the value of the x value of the point, we state it as a equals negative 1. Okay, now we're not going to put a equals negative 1 in yet. We're just going to simplify all of this all the way down to some neat little expression at the end, and then we'll substitute in the negative 1 for a. Okay, so first of all, expand out a plus h all squared, please. So we get a squared plus 2ah plus h squared, and we'll simplify this, we'll expand this out, so we get plus 4a plus 4h minus 3. And at the same time, what we're going to do is we're going to expand in that negative 1, which will change all the signs inside the bracket to negative a squared minus 4a plus 3. Okay, so that step is the expand and remove brackets. Then what we're going to do is we're just going to simplify, and so we've got the a squared plus 2ah plus h squared plus 4a plus 4h minus 3. Well, that plus 3 and the minus 3, they cancel. The negative a squared and the positive a squared, they cancel. And we've got the 4a and that negative 4a, and they cancel. Okay, then we simplify, and what's left over then is 2ah plus h squared plus 4h. Okay, now it's very important at this step, very important that you have to check to make sure that every single term in the numerator has at least one h in it. Okay, that's going to be very important. If that's not the case, then something went wrong up here, or up here when you expanded. Okay, so this step must contain at least one h in each term of the numerator. Then what we're going to do is we're going to factor out an h from each of those terms, and we'd be left with 2a plus h plus 4. Okay, now we'll simplify here, reduce down the h's, and then we're left with 2a plus h plus 4. Now we substitute in a equals negative 1, like we had up here at the top. And so then our expression for average rate of change is 2 times negative 1 plus h plus 4, and when we simplify this, we get 2 plus h. So instead of using the slope formula over and over and over again, we have now reduced that slope formula down to this very simple expression 2 plus h, which now we're going to use to find the average rate of change in the preceding and following intervals. Now, we're still not at the estimate of the instantaneous rate of change step just yet. All we're doing is we're finding the average rate of change for the preceding interval and the following interval. That's all we're doing just yet, just the average rate of change. So we're going to take very small values of h and add them to 2. So first, for the preceding interval, h is going to be negative because it's going to be on the left side of that point. So if I were to look back here, if h were negative, it's going to be over here to the left of our key point that we're looking at with a. And for the following interval, it's going to be a positive value of h to be to the right side of that value of a. Okay, so now what we're going to do is just sub those in. So negative 0.5 plus h, or sorry, is h, and that plus 2 gives us 1.5. Then when we plug in negative 0.1 for h, we add that to 2, we get 1.9. Then when we plug in negative 0.01 in for h, we add that to 2, we get 1.99. And guess what? We're going to go to 0.001 and get 1.999. That's the accuracy I would like you to go to, okay? 3 decimal places. And then for the following interval, we're going to take 0.5, add it to 2, and get 2.5. Then we're going to take 0.1, add it to 2, and of course get 1. Then we're going to put in 0.01, 2.01, and 0.001, and get 2.001. So the estimated instantaneous rate of change is now the average of the last 2 average rates of change. Okay, so what we're going to do is take these last 2 average rates of change and average those 2, and that will then give us the estimated instantaneous rate of change. At this stage, it is not the estimated instantaneous rate of change just yet. So we get to 1.99. Notice how the average rate of change is slowly increasing as h gets really, really small in the preceding interval. The average rate of change is going from 1.5 to 1.9 to 1.999, and so that's going up towards 2. And in the following interval, as h gets really, really small, the average rate of change is 2.5, 2.1 is going down towards 2. Okay? And then the last thing we have to do now, just to finish things off, is the estimated instantaneous rate of change is 1.999 plus 2.001 divided by 2, and that gives us 2. And like the French say, voilà! That is the estimated instantaneous rate of change. Okay, so in summary, there are 3 main methods to determine the estimated instantaneous rate of change. First of all, the preceding and following intervals, which I quite like. Secondly, the centered interval approach, which I'm not the hugest fan of. And the third one, which I really love, is the difference quotient. Now this one, the difference quotient, is generally very, very powerful only when things will cancel out nicely in polynomials. If we don't have polynomials, if we have an exponential or a sinusoidal curve, the difference quotient won't really help much because it doesn't really trim down nicely like this one did, down to an average rate of change of 2 plus h. But I do like the difference quotient, and it is very powerful to save you some work in the long run. So here's your work for today. Please work on the first few at home right now, and then we'll see you in class tomorrow to finish them off.